Hello and welcome to the next installment of Introduction to Three-Phase Electric Circuits. In this second video, we'll be looking at sources feeding loads. So let's get started. First, let's review what we discussed and talked about in our previous lesson. In our previous lesson, we looked at the two different configurations for three-phase circuits, the delta and the Y. When we examined the delta, we said it was sort of like a parallel circuit, in that the phase voltage and the line voltage were the same. But currents were different, where two phase currents would add together to 120 degrees to make up a line current. So at 120 degrees, the line current is bigger than a phase current by a factor of √3, if the circuit is balanced. So too, the phase current will be smaller than the line current by a factor of √3. When we examined the Y circuit, we said it was sort of like series, where the line current and the phase current were the same. But two phase voltages came together to add up to a line voltage. If the system is balanced, then the line voltage is bigger than the phase voltage by a factor of √3. And equally so, the phase voltage is smaller than the line by a factor of √3. At the end of our discussion, we also examined the calculation for power in a three-phase circuit. And we said we could calculate power one of two ways. Either the total power is equal to √3 E line I line, or the total power can also be equal to 3 times E phase I phase. So now that we have that review, let's carry on. Here's our generator again. Again, we have a north-south pole giving us a magnetic flux. And then we have a bunch of coils, 3 sets of coils, 1, 2, and 3, all separated by 120 degrees of separation. From our early discussions back in AC, we know the amount of voltage that is generated is directly proportional to the amount of flux, the speed of the cutting action, and the number of turns. The important thing to remember for this lesson is that our generator gives us our voltage. And since we have 3 coils separated by 120 degrees, we end up with our 3 voltages, all separated by 120 degrees. Our generator, or our source, supplies and sets our voltage, as well as the frequency at which our voltage is given to us. Here's a simplified AC circuit, where we have a 240 volt 60 Hz source. Again, the source supplies our voltage. How much current is drawn is totally dependent on the load that we hook up to the source. In this particular example, we have a 12 ohm load, represented by this motor, hooked up to our 240 volt source. That'll give us 20 amps of current draw. If we were to change the load, we would then change the current. But the source, the voltage, would remain the same. That's an important concept to remember as we move forward. The amount of power dissipated by the load is based on how much voltage is supplied and how much current is drawn. So the load will require 4.8 kVAs. The source must be able to supply that much power. So the source power must equal the load power. So if our load requires 4.8 kVAs, then our source also must be able to at least supply 4.8 kVAs worth of power. Here we have a Y-connected load. And because it's a Y, current's common, but our line voltage is bigger than our phase voltage. Remember, our phase values are inside. So here we have phase A, B, and C. Our source must be able to supply enough line value in order for us to achieve our phase voltages. So now let's take a look at a source feeding a load. Our source will be a delta connected generator, and it's going to supply 400 volts at 60 Hertz. Now since it's a delta, line voltage and phase voltage are the same. Let's connect this source, as you can see is indicated by the circle around the coils. That indicates that it is a source. That source is connected to a Y-connected set of resistors, where each phase resistor is going to be 20 ohms. The easiest way to go about solving these is to break it up into two separate pieces, a source piece and a load piece. Now I've labeled them source and load, both being delta and Y respectively. And that's so I can remember the relationships for deltas and Ys. So for my source delta, I know that line and phase values are the same, which is going to be 400 volts. Now a line value is a line value. It's independent of the shape. So that 400 volt line value gets carried over into my load. But since it's a Y-connected load, and all of my resistors are a phase value, I need a phase voltage. So we'll use our line value of 400 volts to calculate our phase voltage to be 231 volts, approximately. Now that you got your phase voltage and your phase resistance, you can calculate your phase current, which in our Y-connected load will be approximately 11.55 amps. What else do we know about Ys? Well, the line current and the phase current are the same in a Y. And so our load, just as it did before with our motor and our generator, our load sets the current. That means our source has to be able to supply the line current of 11.55 amps. So since it's a delta, and we have a line current 11.55 amps, that means we can now calculate the phase current in our delta generator. So inside our delta, each coil must be able to supply 6.67 amps. Since we have all our currents and our voltages, we can start calculating our powers. So in our load, I'll use root 3 E line I line, which in this case works out to be 8,002 watts. The source should be the same power, because whatever the load is consuming, our source must be able to supply. Now keep in mind, I am ignoring any line losses at this time. Just to verify my calculations, I'll use the phase values on my source, and I'll use 3E phase I phase, and sure enough, when we calculate that all out, we end up with the exact same powers. They match. So our calculations are probably correct. For our second example, let's keep the values the same, but let's change the shapes. For the most part, the procedure is pretty much the same. So we'll keep our 400 volt 60 Hertz source, but we'll change the configuration to a Y-connected generator. And keeping the theme, we'll maintain our 20 ohm resistance per phase, but we'll change the configuration into a delta. So we have a Y-connected source running a delta load. Our source sets the voltage. So our line voltage is 400 volts as indicated. That means that our load will also have a 400 volt line value. But since our load is a delta, E phase and E line are the same, so our phase voltage is also 400 volts. Since we have our phase voltage, we can calculate our phase current, which works out to be 20 amps per phase. But since it's a delta, two phase currents will come together to give us a line current, and since they're balanced, we can multiply through by root 3, which gives us a line current of 34.64-ish amps. Having our voltage and our current in hand, we can calculate the total power dissipated by the load. PT equals root 3 E line, and that's going to give us approximately 24 kilowatts. Depends on how you round. Now that we've set the current, or our load has set the current, of 34.64 amps for a line current, we know that in a Y, the line and the phase current are the same. So that means our Y generator will also have a 34.64 amp line and phase current. But since it's a Y, it has a different phase voltage. So if we take 400 divided by root 3, we end up with 231 volts per phase in our generator. We can now use our phase calculation to calculate our total power and compare that to our load power. And again, ignoring any line losses, they should be the same. And sure enough, when we calculate with the power, where PT is equal to 3 E phase I phase, we again arrive back at our 24 kilowatts. These two should be the same when we do our checks. So what did we cover today? Well, we looked at our delta and we looked at the Y configurations. You have to keep track of them, where your delta is sort of like parallel, where your line and phase voltages are the same, but your currents are different. Your Y is sort of like series, where the current is the same, but the voltage is add. Power can be calculated either way, either root 3 E line I line, or 3 E phase I phase. When it comes to sources feeding loads, it doesn't matter if your source is a Y or a delta, and it doesn't matter if it's a delta feeding a Y or a delta feeding a delta or a Y feeding a Y or a Y feeding a delta. The procedure is the same. Your source sets the line voltage, so you need to find the line voltage first. You then carry that line voltage over to your load. Then you will need to find the phase voltage. And once you've found the phase voltage and you have your phase opposition, you can calculate your phase current. Now, depending on the shape, you may have to adjust your line current. Once you have the line current, you can then take that back to your source from your load. Remember, your load sets the current, your source provides the voltage. So you set your line current according to what you found in the load. You can now calculate the phase current in the source, and you can also find the phase voltage in the source. Having all your voltages and your currents in hand, you can now calculate and compare your load powers. That's just a good practice to make sure that your work is working out. And that concludes this presentation on sources feeding loads in a three-phase circuit.